Okay, so in this video, we just looked at the power set, right? And now we want to see that there is actually a hierarchy of sizes of infinite sets. So that's what we're going to do in this video. But before we do that, remember that if A is a set whose cardinality is finite, then the size of the power set of A is equal to 2 to the size of A. In particular, the power set of A is always strictly bigger in size than A. So now the question is, what happens if A is an infinite set? Yeah, we've already seen like many examples where just because you're an infinite set doesn't mean you know lots of bizarre things can happen. So we have to be careful about our intuition here, and in particular, um, we have seen that um, the natural numbers are the same size as the natural numbers cross the natural numbers, which are the same size as the rational numbers. So, you know, these things are not what we would have expected, I think, from the beginning, but now we've gotten some familiarity with this. So we have to be careful with infinite sets. So we don't have great intuition. And that's why we make a rigorous definition that two infinite sets are the same size if there's a bijection between them. And now we're going to prove a theorem which will help us make sense of different sizes of infinite sets. So the theorem says the following. If A is a set, then notice I don't need to say infinite set. This will be true regardless. Then A is strictly less than the size of the power set of A. So the cardinality A is always strictly smaller than the cardinality of the power set. We already knew this for finite sets, but notice then for infinite sets that that's saying that if you start with the naturals and then take its power set, you get a strictly larger size, uh, a strictly larger cardinality than the naturals, right? Okay, remember that the power set is a set of all subsets here, right? Okay, so now let's look at this proof. This is another famous proof. This is given by Cantor. We've already seen Cantor's diagonalization argument, and this is going to be a version of his diagonalization argument, but now you can't draw the diagonalization. You have to come up with a clever way of defining the diagonalization. So I'll show you what I mean by that. Let's get in the proof, okay? So the proof will follow a similar strategy in the sense that we're going to do this by contradiction. And so um, let's assume, for sake of contradiction, that so we got to assume the opposite, right? So that the power set, or sorry, so that the cardinality of A is bigger than or equal to the power set, the size of the power set of A. That's the opposite, right? And that's going to lead to a contradiction. In other words, assume there is a surjection F from A to the power set of A. Now, I didn't define this, but I'm going to explain it here so that you're comfortable with it, hopefully. But we said that two sets have the same cardinality if there's a bijection. Now, what's also the case is that if there's a surjection from a set A to something else, then I can also compare their sizes. And that means that the size of A must be bigger than or equal to. First of all, I could have said it's a surjection, but it might actually be a bijection, in which case they're the same size. But then let's say it is a surjection, but it's not an injection. Then that means that A maps onto the power set of A. So for every element in the domain, there is a corresponding buddy but I may have doubled up some people from A, right? So I may have doubled up lots of different values from A, which means that A could possibly have a larger size, right? So that's why if you assume that one set has bigger than or equal to the other set, then a way of saying that in terms of functions is to say that a surjection exists from A to its power set. Okay, so that's why I'm allowed to do that. Okay, so now let's just remember, since F is a surjection, um, for every um, subset T, there exists a T in the A. So for every capital T is a subset, there exists an element, little lowercase t, so that F of lowercase t is equal to capital T. Okay, again, remember the function starts with elements of A and returns a subset of A, right? So it's a nice notation to use the lowercase t for an element of A and the capital T for a subset of A, right? So now we will construct, well, construct is probably the wrong word. We're going to describe, I guess, a set B, which is a subset of A, which cannot be an image of an element of A under F. So that's what we're going to do. Again, you have to see, you have to ask me how, right? But we're going to show you in a second. But notice this is following the idea of Cantor's diagonalization argument. You assume that there is, in this case, you assume that there is a surjection. It's sort of like assuming that you could list out the elements of the real numbers, but then you're going to produce another um, subset of A, or in other words, like another real number that's not already in your list, right? So in this case, we're going to produce a subset which couldn't be defined in our surjection, and so that's going to give a contradiction, right? There's going to be some subset of A that could not have been an image under this map, and so it must not be a surjection, in which case we get the conclusion that we want. All right. So let's see what we get, right? So now remember that for any element of A, we know that, well, this is just by definition, f of A is in the power set of A, and hence, just trying to really walk you carefully through this without going too fast. So we can keep track of whether or not, oops, trying to give you some intuition for what I'm about to do, because I don't want it to feel like I'm pulling it completely out of a hat here. So what we're saying is that because of the way this function is defined, you take elements of A and you send it to a subset of A. So you can ask, is the original element A inside of the subset of F of A? And so that's how we're going to define this set that's going to cause problems. So to this end, we define the set B that's going to be the causing problems, okay? So B is the set of all A in A, so that A is not an element of F of A. All right. Now, this is supposed to be similar to Cantor's diagonalization argument here. And so you think of F of A as sort of like the listing out of the elements of the real numbers. And by choosing A that's not in its subset, it's sort of like changing the diagonal in that proof. Okay. Now, this analogy is not necessary to understand the proof, but I think it's interesting. So here's the set that we're going to use, and then I'm going to make a claim, which is going to bring us home here if we can carry out this claim. So there is no lowercase b so that f of b equals b. Sorry, not, I said that wrong. That wouldn't quite work, right? I want to say there's no lowercase b in a, so that f of b equals capital B. Okay, so this is the claim. If we can pull this off, then that's what it means. Then we show that the function's not surjective, which is contradiction, and we're done, right? So let's see how to do this. So this is also going to be done. This claim is going to be done by contradiction as well. So assume, for sake of contradiction, that. Oh, by the way, just to be clear, the way this set B is defined, it has to be a subset of A, right? Because it's just the set of all elements in A that satisfy an additional requirement. So just want to be clear that it's a subset of A. So we already know it's a subset of A. It's the kind of thing that lives in the power set of A. And so we want to show that it's not the image of anything under this map, right? So just another way of saying this is that B is in the power set of A. Okay, good. So assume for sake of contradiction that there is some B in A so that f of lowercase b is equal to this set. By the definition, of B, we see that, well, B is in B if and only if, well, what does it mean to be in this set? It's in there if and only if, let me just write that out instead of using the shorthand, if and only if. Well, it has to be, by definition, not in f of B. Okay, but notice that we've already assumed that f of lowercase b is equal to capital B. So since f of lowercase b is equal to capital B, this is equivalent to, well, this is equivalent to, we can trade out the b in the first part for b is in f of b if and only if b is not in f of b, right? But that's a problem, which, I mean, it's a contradiction. Hence, there is no such surjection F, and it must be the case that the size of A is strictly less than the size of the power set of A, which is what we wanted to prove. Okay, so this contradiction feels like Russell's paradox, but this is not it's not a paradox here. It's just that, I mean, the set is completely defined. There's nothing wrong with this set per se. It's just that there's something wrong with the surjection. There's a contradiction in the surjection, and then, but we don't get like some paradox that ruins set theory here. We just get a contradiction, and hence we've proven that the size of A is strictly less than the size of the power set of A. And now there's an important corollary to this, which is kind of the whole reason why I did this. So again, it's a diagonalization argument, though, because we produce an element B, which has to be in the codomain that could not be mapped on to by the domain. And we did that by like producing some set that couldn't by definition be allowed, right? But this condition saying that A is not in F of A is like the way of trying to mimic the diagonalization argument where we change the elements of the diagonal. That's sort of the idea there. Okay, but the important corollary to this is the following. So corollary. There exist infinitely many distinct infinite cardinalities, which is like a hierarchy of sizes of infinite sets beyond just countable sets, right? So the way to do this, I'll even do the proof. It's a simple corollary, so the proof is quite. I mean, I stated the corollary not so specifically, so I'm just going to do the following, right? So by the previous theorem, there exists the just going to exhibit following chain of distinct infinite cardinalities. So there's the size of the natural numbers, which is strictly less than the size of the power set of the natural numbers, which is strictly less than the size of the power set of the naturals. Notice you can take the power set twice because the power set is a set. And so it has a set of subsets, right? And you can keep doing this. This is basically the point. I'm not going to write them all out. I'll do one more. So I can take the power set of the power set of the power set of the natural numbers. Can keep going. And that is a hierarchy of different sizes of infinite cardinalities, right? So there you go. You already see now that there has to be a whole different hierarchy of these sizes of infinite cardinalities. And now you can ask questions about like, what is that hierarchy like, right? Okay, the size of the naturals is strictly less than the power set of the naturals. Is there something in between, right? Or is there a whole continuum in between? Like, you don't know, right? At this point, we don't know exactly what the structure is here. And an important question, which is related to the continuum hypothesis, is what is the relationship between the size of the power set of the naturals and the size of the real numbers? So this is another way of talking about the continuum hypothesis. And well, you can't decide this actually. So it turns out that oh no, sorry. This you can sorry. This is I'm saying that the wrong way. So this you can actually show. So you can show that the power set of the naturals is the same size as the real numbers, and that's different than the continuum hypothesis. But the continuum hypothesis, it can also be stated in terms of the power set of the naturals. Okay, great. So now what I wanted to do in this video, though, was to show you that there are a whole hierarchy of different sizes of infinity. So that's what we've done now. And then later, in the future, I will show you how to play around further with this and talk about the ordinal numbers and the cardinal numbers and various different things you can do discussing this further.